Usually when we think about continuity in a function, we think about a function that is like a smooth curve where we can go from one side to the other without picking up our pencil. This is a decent understanding of continuity, but really we need to be a lot more specific when we talk about continuity, both at a point and on an interval. So this is one of those things where we need to know the precise definition, not just a general idea. And you will have questions that ask you that evaluate whether or not you know the precise definition, like does this satisfy all three conditions, that kind of thing. So make sure that you know these precisely. Okay, so the first condition for a function to be continuous at a point, so this is at a point, okay, is that the point has to exist. So f of c must exist. Okay, the second condition is that the limit exists. So the limit as x approaches c of f of x must exist. And then lastly, for a function to be continuous at a point c, the limit and the value of the function have to be the same. So the limit is equal to f of c. Okay? And we'll see some examples of various ones where, like, maybe they don't satisfy the first part, or maybe they don't satisfy the second part, etc. Okay? An example of something that is discontinuous because it doesn't satisfy the first would be something where we have a hole. Okay? So in an example like this, we have a limit at this point, whatever this c value is, but we don't have a point, so the function is discontinuous at that point. We also could have something where we have a where the second part is not satisfied, but the first part is. So for example, a step function. Okay, so f of c does exist, but the limit does not, so it is not continuous at that point. And then we could have things where the limit exists and the point exists, but they're not equal to each other. So something like this, where the point is elsewhere. The point exists, the limit exists, but they're not equal to each other, so the function is not continuous at that point. Okay? So that's continuity at a point. We also need to look at continuity over an interval, okay? And so we're going to start with an open interval, and we're going to be real specific about the endpoints we use here. So f is continuous on the open interval from a to b if, and remember this is if and only if and only if f is continuous at x equals c for every c in that interval. Okay, so every point inside, not including the endpoints, every point inside here, every value of c that we could put in there, the function satisfies these three conditions. Okay, just a quick visual. So we've got a and b, and it doesn't really matter what's happening at the endpoints. Okay, they could be open circles, but something like this would satisfy this condition for continuity on the open interval, because every point in between here would satisfy all three of these conditions. Okay. For part B, we have that f is continuous on the interval that is open at a and closed at b, if and only if it's continuous on the open interval, so satisfies the first part. Also, the limit as we approach b from the left is equal to the value of the function at point b. So in other words, we're not satisfying, we're satisfying this condition in a one-sided type of way. So let me give you a sketch here. Okay, so we could have something like this, where f of b does exist, and the function is continuous everywhere in between a and b, and then the limit as we approach b from the left is equal to the value at b. Therefore, it's continuous on the interval that is closed at b. All right. Similarly, f is continuous on the interval that is closed at a and open at b, if and only if it's continuous on the open interval, and the limit as we approach a from the right is equal to the value at a. Okay, so something like this. So here, continuous everywhere in between, and the limit as we, sorry, hold on. Sorry, I lost my train of thought with a barking dog. Okay, this is this is continuous everywhere in between a and b, and the limit as we approach a from the right is equal to the value at a. Okay, and then lastly, the function is continuous on the closed interval if and only if it is continuous on both of these intervals together. So something like that, closed on both ends. Okay, so we'll do one example here, and then I'll probably break and do another video for the rest of them. Okay, so are these functions continuous on their domains? All right, so this right here is an interesting phrase. Here we need to consider the domain of each function, and then if not, we want to describe any points. So where would the function be discontinuous? But domain does matter. So for example, if something is not in the domain, then it doesn't. If x equals 5 is not part of the domain, it doesn't really matter what happens at 5, okay? All right, so for the first one, we have y equals x over the absolute value of x. And you may have seen something similar in some chapter 0 homework problems. My recommendation for a problem like this is to split it as a piecewise function, all right? So before we go any further, I want to define absolute value of x real quick. So absolute value of x is defined as a piecewise function x when x is greater than or equal to 0, and the opposite of x when x is less than 0. Okay, so if I have anything else that involves absolute value of x, I can split it as a piecewise function. So for this one right here, I'm going to write this as x over, and then as long as x is positive, its output is the same as its input, okay? When x is greater than 0. Note that I am not including 0 because 0 is not part of the domain, okay? And then x over the opposite of x when x is less than 0. All right, so reducing that, we get 1 when x is positive, -1 when x is negative. Okay, and if we want to think about what that graph looks like, we have something like this. Okay, so is this function continuous on its domain? Well, the domain is every point except for x equals 0. All right, so is this function continuous right here? Yes. Is it continuous right here? Yes. Is it continuous here? Yes. Is it continuous here? Yes. Is it continuous really, really, really close to x equals 0? It is, because we could get even closer and have a limit coming from the left, okay? Same thing down here. So we can say that yes, this function is continuous on its domain. Now, if we just had a general understanding of continuity as we can go from one side to the other without picking up our pencil, we would have a problem there, okay? Because we can't draw this graph going from one side to the other without picking up our pencil, okay? But because the question says on its domain is the function continuous, the answer is yes. Okay, for this next one, we're dealing with the step function, the greatest integer function. So just a quick sketch here. Okay, something like this. We see that the domain for this is all real numbers, because every real number can be plugged into the greatest integer function. However, it is not continuous at every point on its domain. Okay, so here we would say that it is discontinuous at, and we can just say this in words, we could say at all integers. It's continuous at every non-integer point. All right, and for the last one, y equals 1 over x, this is going to be pretty similar to the first one. Thinking about the shape of its graph, because the domain does not include x equals 0, we do not need to consider that as a point of discontinuity. Now, if the question said, where is this graph, where is the graph of 1 over x discontinuous, then the answer would be at x equals 0. But because it specifically says, is it continuous on its domain, then 0 is not in consideration. So if 0 is the only point of discontinuity and 0 doesn't get counted because it's not in the domain, then this function is continuous everywhere on its domain.